find that YouTube URL in the description. And that was conducted by GDG and TFUG Mysuru in previous session. And in today's session, we'll be actually focusing more on the advanced concepts of image processing techniques. We'll be building a deep neural network and try to improve that in a much more efficient way. So about me, I'm Vivek Raja and I'm from Madurai, Tamil Nadu. I've graduated from Mepcloshank Engineering College in 2020. And I started working as a data scientist in a startup called NexStem. I'm AWS Machine Learning Hero, which is a part of Heroes program from Amazon Web Services, which is one of the recognized as in each domain. And I'm also an organizer at Azure Develop Communities in Tamil Nadu, which has over 3,000 members. And I'm also co-organizer and active member in AWS User Group, Tensorflow User Group, GDGs, and Tamil FOSS communities. And I am 16 times multi-cloud certified as Microsoft certified data scientist, AI engineer, data engineer, and developer associate. And I am Oracle Cloud Solution Architect as well as Alibaba Cloud Expert. I've also published a lot of research papers and an active speaker, mentor, and a blogger as well. So the agenda of these complete two-part series is about learning what is image processing and the use cases associated with it. And we have also seen what the challenges we have involved in the image data processing. And then we took over on taking a simple basic classification problem to understand the machine learning workflow that involves in image data processing and a hands-on session along with that. So in this second part, which is brought to you by GDG Mysuru and TensorFlow User Group Mysuru and Women Tech Makers, and the industry partners are Jarvis Lab AI and JetBrains. And this is second part of that Zero to Hero image processing technique series. So to summarize what you have learned in previous session is like we understood what is image processing and why it is important. And we also saw what are the challenges we faced while implementing the same. We also understood like how to work in an image data analytics problem and what are the steps which is involved in it. And in that particular steps, we try to identify the data source, we collected and organized the data set. We also loaded the data set in a memory efficient way. We standardized it. We created a simple CNN model and trained a particular basic classification model. And in this particular session, we'll be seeing how to create a better CNN deep learning models and understand how it works, and we'll try to improvise the same. To load a particular data set, so it's imagine you are working in an image data set, and image problems are always of higher resolutions and high memory space. So it's impossible to import all those image data files at once. To efficiently load a particular data set off disk, there are a couple of ways how to do that. And in today's session, we'll be actually seeing how to classify the images of flowers. So there were around 3,700 photos of flower, and it has 5 sub directories and one for each class as well. So we have created these particular data set from image data set from directory utility, and this will take you to the directory of images on the disk to a dfdata.dataset with a couple of lines as well. And it's always a good practice to split the dataset into 80% as training and 20% as validation. It's just a thumb rule, and you can go with any percentage as you prefer by. So let's get started with that. And we'll also follow the earlier procedure of how to standardize and build and train the model as well. So first, let's import all the necessary TensorFlow libraries and other libraries which is involved in it. And we will download and load the dataset in particular format. So the flower photo represents the total directory, and it has 5 classes, which is each for one class, which is daisy, dandelion, roses, sunflowers, and tulips. So this dataset is obtained from a dataset URL, which is flower photos, and we try to extract it and arrange that into 5 subdirectories. So, and once the data is loaded, we'll be able to print the data directory, which is like the root, keras datasets.flower photos, and let's try to count the total image value. So it has around 3670 to be precise, and let's pick out some of the images from each classes. So I'm trying to load one of the images from the class rows. So it looks something like this and so on. And this is from tulip and so on. You can check out the other subdirectories as well. So now coming to the concept of how to load and create a particular data set. So let's try to set some parameters for the loader. So let's try to load the images in the batch size of 32, and let that image and height can be set to 180 cross 180. And of course, since we are also trying to set 80% of the images as training and 20% for the test data set, we'll also do it as well. So to create our test dataset, what we are trying to do is we are using tensorflow.preprocessing.image dataset from directory, and we're passing the data directory in such a way like the subdirectories represents each classes, and each classes has the images associated with it. And the validation split is 0.2, which represents 20%. And we are naming this subset as training, and the image size is set into 180 cross 180, and the batch size is 32. So this has found 3670 files belonging to 5 classes. That's true. And by splitting 80 cross 20, we have got 2936 files of training dataset. And of course, when we follow this for validation, and we find 734 files for validation. So let's try to print out the class names, which is nothing but the 5 subdirectories, which is daisy, dandelion, roses, and sunflowers and tulips. And let's try to visualize the data. We are going to use matplotlib library for this, and this is how the classes looks like. And to train a particular model, we need to pass it to model.fit, and it has got 32 batch size of 180 cross 180 cross 3, and the 3 actually represents the RGB color channels. So to make sure that we configure the dataset for better performance, we can use cache and prefetch. So that actually keeps the images in memory after they're loaded off the disk during the first epoch. So that actually improves your performance and your memory utilization in a better way. So we are going to use that as autotune, and we're going to shuffle, and we're going to prefetch the dataset in buffer size of autotune. And to standardize the dataset, as you've seen in the first part, we divided that RGB values by 255, which will actually give you all the ranges between 0 to 1. So let's keep this particular layer as a rescaling layer, so which is a normalization layer, which is I'm keeping at normalization layer, which is equal to layers.preprocessing of rescaling of 1 by 255. So we're going to normalize all the values between 0 to 1 for better processing. And then after we create a data set out of those normalization layer, this is how a maximum and minimum value looks like. So the minimum value is 0 and the maximum value is 1 after standardization. And now let's jump back to the basic training the model. So these are the steps which are already discussed in the part 1. So this is just nothing but a recap, and let's go with the simple model training approach. So we are going to build a CNN model. In last session, we have seen about building a simple CNN model with 3 layers, which is a flatten, dense, and output layer. So in this, we'll just extend the CNN model in a better way to make sure that we can bring out a better result. And we'll try to understand what that each layer looks like and what each layer does. So the first layer is the rescaling layer, which is the normalization layer, where we rescale it all the values by dividing it by 255, and although the input shape is given in form of 180 cross 180 cross 3, and we are placing that in forms of convolution 2D layers and max pooling layers in such a way. And of course, we are much more familiar with these lines in line number 11, 12, and 13, which is the flattening and dense layer, which has the activation as ReLU, and the final dense layer represents the output layer, which is number of classes, which is 5. So Now we have inserted a couple of more layers for better prediction. Let's try to understand what that each means. So before that, let's try to compile the model, and this is also much more familiar with us from the previous part of thing. We have learned about Adam optimizer, and we also learned about the loss function which is involved in it and the metrics as accuracy. So let's compile the model and see how it goes. This is a model summary. And once we train the model, what you have noticed is like the loss at the first epoch was around 77%, and it has drastically reduced to 0.03%, which is I'm sorry, like the first was 77% and it has reduced to 3% at the end of 10 epochs. And also if you notice, the accuracy has improved from 70% to 99%, which is a sign of a good training model. But when it comes to validation accuracy, there is some catch. So the validation loss has increased from 90%, or if you can say, put into simple words, like 0.9 to, and it increased to 1.7, which is the loss is increasing, and the validation accuracy has decreased from 65% to 63%. So what has actually happened in this particular results? So let's try to plot it in a graph to learn it much more better. So the validation and training accuracy in such a way, like the training accuracy improved, but the validation accuracy decreased, and the training loss decreased, but the validation loss increased. So which is not a good sign, right? So what we infer from this particular is like the model has been overfitted, in the sense it has learned pretty well about the training dataset, but it failed to learn about the unseen data. And we will also see how to overcome this process, but before we go into that, we will learn about what are the new concepts which we are seeing in this current CNN model, which is we have included conventional 2D layers and max pooling layers as well. So let's try to understand what those layers perform. And we are very well aware of the other three layers, which is flatten and dense. Flatten and stacks the two-dimensional or three-dimensional into one single one-dimensional layer, and dense is nothing but a fully connected layer, as we seen above. So let's jump back and learn the concepts before we carry on. So a conventional 2D layer, as before that, we need to learn a couple of concepts which is involved in it. So the first step is that a k kernels waiting to be applied in an image, and each kernel is convolutional with input volume, and the output of the each convolutional operation produces a 2D output called activation map. So these are the three steps which is involved in it. So what is happening is like the kernel gets applied in each steps of the image, and it gets multiplied. For example, in this particular sign, it is multiplied with a particular value, and once that is done, we sum it and we try to get the summation value. So the first one is 4, 3, 4, 2, 4, 3, and it goes on. So now I'd like to analyze what it really happens. In the stride 1, it moves in as stride 1 by 1, and it tries to get the feature map for it. So the stride actually represent how much we move the convolutional filter at each step. So in this value, we can see it is moving one step at a particular time. So the stride is 1, and to make sure that it does not again involve in overfitting or sort of stuff, we use padding. So padding is nothing but to preserve the size of the feature maps that would shrink at each layer, which is actually not desirable. So what we do is we pad the outermost pixels in the image, and we move on with the stride as 1, so that the feature map remains large as an end of each convolution, so that we try to preserve the size of the feature map as we pass it out to different layers. As compared to the stride 1 without padding and with padding, we can see there is an increase of the feature map from the size of 3 cross 3 to 5 cross 5, which is actually a good sign. So now that we understood, like now let's try to understand what the max pooling layer actually performs upon. So the max pooling layers is applied to reduce the dimensionality. So for example, if you're dealing with a big image. And for example, if you're also applying a stride with padding, which will also give you a big feature map, to reduce that dimensionality, we use max pooling layer. So here the max pooling is done with a 2x2 window with a stride of 2. What happens is, like, as a stride of 2, which means it moves 2 steps at a particular time. So in this, it takes 2x2 as a max pool, and in this particular, which is an orange region, what is the maximum number we find in it? That's 6. So we put it as 6, and it moves stride as 2, so 2 steps away from it. So we have a green color padding, so a window, and the green window has 8 as a maximum, so we'll place it. And again, the stride is as 2, and we move down and we have this yellow region, which is 3, 2, 1, and 2. So 3 is the maximum, 1, 0, 3, 4, and 4 is the maximum in the blue pool. So we have reduced the dimensionality in such a way, like we moved in a particular stride and we found what's the maximum value in the each feature map. So this actually enables to understand or makes the machine learning problem much more easier for the model to learn, and also it's very much efficient to reduce the dimensionality as well. So now let's try to understand like what happened, and we also discussed this is a problem of overfitting because it has performed very well in the training dataset and does not perform well in the validation dataset. To overcome this overfitting, what we'll try to do is, there are a couple of ways to perform it. So one is data augmentation, and the second one is dropout values. The first one is data augmentation, in which you pre-process the image so that the image is served to the machine learning model in a better way for the model to learn, so that it does not has to it can overcome the burden of understanding complex images. And the second one is dropout layer. So let's try to understand the pre-processing images, and it falls under two categories. One is morphological transformation and one is data augmentation. So what does morphological transformation looks like? So morphology is nothing but you do in terms of it involves some shape and form. So whatever you that morphological transformation actually implies that you modify the shape and form of an image. So there are a couple of ways to do it. One is thresholding. It's like you keep a particular threshold of the pixels, and whatever above that particular threshold is converted as 1, and below it converted as 0. So obviously this will result in a binary image. And erosion is where it shrinks the bright region and enlarges the dark region, and dilation is an opposite to it. And opening is closing is applying dilation plus erosion, and closing is applying erosion and dilation. To know much more about these transformations, which you're not going to learn in today's session, but this source code will be available at the end of today's session. You can go back and run to see the differences of how these morphological transformation looks like. And data augmentation. So at the beginning of the first part of the session, we addressed a particular challenge, which is like and each image needs to be viewed in a lot of angles and illuminations and so on. So that actually helps us to understand a single image in a much more better way. So to understand, to overcome those challenges and to address the overfitting problem, data augmentation is a very good solution. And data augmentation is like flipping, rotating, cropping, translating, and adding noise and illumination to the image to make sure that you generate a lot of image for a particular single input of image, and you make the model learn all the variations. So for this, you can refer to this particular Python notebook to learn about pre-processing images. For the shortage of time, we will move on to the concepts and we'll proceed with it. So now that we discussed about how to prevent overfitting by data augmentation and dropout, now let's understand about dropout regularization. So we have learned something about dense layers. So a dense layer is nothing but which is a layer of machine learning which has a number of neurons, and each neuron is well connected to all the neurons in the previous layer and the next layer as well. So that's a particular standard neural network looks like. But a dropout is where you randomly select a particular neurons in a layer and you disable it, so that to make sure that it does not learn all the features and it only learns a random number of features to make sure that it generalizes a particular learning process. So dropout actually learns enables it much more better way. So if you can notice the B image, which is where we have applied dropout, we have disabled the neurons which is marked as red so that it does not pass the information to the next layer. And these are the only input layers that the next layer will be getting the information about, so that we voluntarily make the model lose some of the information to generalize the way of how it learns. So there are multiple regularization method which applies called early stopping, noise, and weight decay, but we can explore it in other sessions, or I will leave it to you to learn it in your free time. But dropout actually works pretty good. So now let's try to implement this and see how the model performance varies. So first, let's try to apply data augmentation. So in this data augmentation, what you're going to do is I'm going to do a random flip of horizontal way. And of course, a flipping can be done both vertically and horizontally. So you're going to just do a random flip on horizontal way. And this is a random rotation of 0.1 degrees and random zoom of 0.1 factor. So this is how some of the augmented example looks like. So which is like this is rotated into 0.1 degrees, and this is zoomed, and this is flipped in horizontal way, and so on. So a single image has been represented in a various way to make sure that your machine learning model learns in a much more better way. So now let's apply the dropout. So this is the same machine learning model we have taken earlier, and we have added the data augmentation layer, which is random flipping and zooming and rotation. And of course, that is followed by the standardization layer, which is descaling it by dividing it by 255 to make sure that we has all the values between 0 and 1. And this comes with the max pooling and convolution layers, which we learned a little bit earlier. And we are introducing the layer as dropout as 0.2, which is we are randomly disabling 20% of the neurons in a layer, and followed by the 3 layers which we are much more familiar with, which is the flatten, dense, and the output layer. So let's try to compile the same this machine learning model layer and see how it works. So this is a summary, and by training we have noticed that the loss, which was in 1.5 at the first epoch, has dropped to significantly to 0.693, and the accuracy has improved from 0.35% to 73% for training dataset. And when it comes to validation loss, it has decreased from 1.12 to 0.78, and the validation accuracy has improved from 52% to 69%. So which is the loss is decreasing and the accuracy increasing, and comparatively the difference between the training accuracy and validation accuracy is very less, which means the model has significantly improved and it has overcome overfitting. So now again, let's try to see the graph between the validation accuracy and training accuracy, which is much more similar in way of how it learns when it comes to training and the validation data set, which is a good sign this model is not overfitted and it is performing very well. So which is actually a good sign that we have overcome overfitting. But is there a better way to improve the model in a much more sufficient way? Yes, there is a way for it. So the approach is called transfer learning. So in previous approaches, we have built the CNN model by ourselves, and we specify the layers and the input layers and what are the layers which it needs to have to perform much more better way. So, but what if a machine learning model is pre-trained in a very large data set, and what if you can just fine tune it in a way so that you can just leverage the already learned models weightage to make up predictions in your particular data set. So to put it into simple words, you transfer the learning which was done in a different data set to your data set so that you can work on your data set without actually having to leverage to train it from first. So this is called a transfer learning approach. And when it comes to fine tuning, it's like you add a couple of layers to it and you fine tune it so that you can increase the performance to your relevant to your particular data set. So let's try to do that here. So first, there are multiple machine learning models for classification, which is like MobileNet, Inception v3, and so on. So Inception v3 is actually a Google's winning machine learning model in 2015 ImageNet conference, and ResNet is Microsoft's number one winning model for the same conference as well. So these has been trained in a very large data set, and we can try to leverage that learnings to apply to a particular data set, which is our flower classification. So the image shape is 224 cross 224 because that is what it has been trained upon, and we have to use the same as well. So we are using the same steps, which is like doing the pre-processing and doing the validation instead. So now let's try to use the classifier model to predict it. So of course, since the Inception v3 has already learned about all those images, which doesn't necessarily need not be the same classes which has learned about. For example, like the image data set which it has learned about might have around thousands of data classes, but it does not necessarily need to be the same data classes what we are trying to classify about. So that's why it has tried to classify in different ways, like coral fungus, which is not even uh, our class which we had. So let's try to visualize it and see what it's like. This is Daisy, which is the correct one because both the classes is common to it. And this has been classified as a green vase, and this is classified as a vase. This is classified as an ant. So we don't really have an ant in our particular data set. To make sure that it only classifies to the class names which we have in our data set. So that's where the fine tuning comes into picture. So what we do is we take the Inception v3 or any pre-trained model, we add a couple of layers to it so that the output layer matches to the classes what we are going to train upon. So we have taken mobile v2, I have added an output layer in which has the same number of outputs as that of our dataset, and I'm going to compile it to see how it works. So we are compiling it, and I'm just running it for 2 epochs to make sure that it does not have much of training time. And when we actually visualize it, it's much more better. And as we've seen about, it is trying to classify to the same classes what the names what we have here, so which is dandelion, roses, sunflowers, tulips, and stuff. And to improve it, of course, we can keep performing the same steps what we had done earlier, which is the augmentation and the dropout. We can still apply to it to see how it works. And to visualize it, we have a much more better way of validation and training data accuracy and the training loss and validation loss. So what we have done is like we learned about preparing a CNN, we improved the overfitting challenge, and then we learned about transfer learning, and we also used a transfer learning in a fine-tuned manner by adding a couple of layers. And of course, we already know about fine-tuning a CNN model by improving it by data augmentation and dropout. We applied the same concepts in transfer learning as well and achieved a better accuracy. So in today's session, we learned about why a CNN model actually overfitted, and we explored the way of overfitting, which is morphological and augmentation. We learned different types of augmentation and saw the output as well. And we also learned about how dropout regularization works, and we included the same in creating and training a CNN model, and we analyzed the results of it. Then we learned about why a transfer learning approach is one of the best and quick way, and we fine-tuned it and we compared the results as well. So before we conclude today's session, we have some more points which can be covered, but I will leave the best to you to go and research after the session ends. So one is feature selection. So what does feature selection actually mean? At the end of each layer of CNN, we got something called a feature map, right? So a feature map might have a lot of features in it, and it's not necessarily that each feature contributes to the particular output. To select that, the features which actually contributes to the output of the model. Those methods are called feature selection methods, and you can look into that. There are a couple of ways to do it, and you can find it as well. So the methods are filter and wrapper methods and optimization techniques. So optimization techniques actually involves optimization algorithms like ant colonies, genetic algorithm, and so on. And filter and wrapper methods are conventional way of doing it. And image segmentation. So one of the primary challenges we saw in the first part of this series is about uh, the background clutter, which is like a measure of your noise, which is available in your dataset, and also occlusion. Occlusion is where most of your targeted image is covered by an unrelated image in the front. For example, we discussed an example where your water bottle is covered by a cat which is sitting in front of it. So image segmentation is where you segment the target images so that your machine learning algorithms can learn much more better way. So you can also refer to the code sample which is given in the link. And of course, when it comes to image, we have only seen about images of real world, but we never saw about any facial related images. So to immediately get started with facial detection and stuff, with the help of what we have learned so far, is you can go to this particular URL, and this actually covers a lot of stuff which you have already learned. And we have actually trained all the machine learning algorithms in local, which is also we use Google Colab for that. And why not cloud? A cloud service provider such as Google, Amazon, and Azure already have much more decent and well prepared computer vision APIs. So instead of you spending a lot of time in preparing a model, you can leverage and leverage the API services which is already available in forms of models. So that's efficient and very time-saving process as well. So the references are given in my GitHub repo, and you can drop your questions in the YouTube channel chat. And this is how you can connect with me through LinkedIn and Twitter at Vivek0712. And these are my blogs and my communities as well. So thank you for today's session, and hope you had a good insight about how to learn do an image processing techniques from scratch in the first part. And we also carried on about creating a CNN model, and we learned to efficiently improve the accuracy for that. So all the code samples are available in my GitHub, and you can